Well, you can see that we moved down onto level ground. Look at me and compare the bike to me. I'm standing straight up and the bike is now perpendicular to me. It's because it's sitting on level ground. Well, let's take this opportunity now to see if any of our forces need to be reoriented because we came off a hill onto level ground. Well, as we continue to pedal, the pedal force will act to carry us along this level ground. So we would expect the pedal force to be parallel to the ground. As we move along the ground, we encounter all sorts of obstacles. We call that friction. So we would expect friction to be parallel to the ground and acting in the direction opposite our motion. So down here, friction doesn't change. Now you can see that I'm standing straight up, which means that gravity is pulling me straight down. Now weight is going to be a vector that does change because we came off of the hill. So I have to turn the weight vector so that it's straight up and down compared to me. Now the normal force again will be the force that's perpendicular to the ground. So if the ground is horizontal, then the normal force will be perpendicular to the ground. So the normal force, which was already perpendicular perpendicular to the pedal force, even though we were on a hill, the pedal force was down, which meant the normal force would be perpendicular to it. So this is the new orientation of our forces. Now this is the orientation of forces that exist when easy riding is being had. You'll notice that the pedal force and friction are in line with each other, and you'll see that the normal force and the weight are in line with each other. Well, the forces aren't complicated. They're related to each other, but in opposite directions. Well, again, this lesson is all about how all four of these forces combine to result in a single action, moving the bike forward. Okay, now that you've seen the process of the application of a free body diagram, a force table, and summation equations, it's now time to walk through 3 complete examples. Now we're going to keep real simple examples and escalate them up to be more and more involved. Now what I want to really iterate is that the process doesn't change. When things get harder, that doesn't change all the rules that we've just talked about. This is set up so that you can handle any level of problem, any level of involvement, and any level of complexity. It's all about forces. When would you use this? You would use this when you are having questions or addressing questions regarding multiple forces and their effect on the motion. So, here we go. This is a ramp on a horizontal plane with a bus. Well, this is about as simple as it can get. So we're going to construct we're going to walk through each one of these examples, first constructing the free body diagram for each one. Then we'll go back and do steps 2, 3, and 4 for each example. So let's get all free body diagrams on the board. 1, 2, 3. Okay, this idea right here, you can't get more simple than a bus. But we do try to make it more simple and eliminate the distraction of the environment. And so instead of practical objects like a bus, we end up using things like a simple cart or a block of wood and some pulleys, and combined, this little playground, if you will, are called Atwood machines. These playgrounds that we make out of planes, little simple carts or blocks of wood and pulleys are called Atwood machines. And their sole purpose is to isolate the concept from the reality, because reality sometimes buggers up our train of thought. Okay, well, here's our physical situation here. Let's draw a free body diagram of this situation. So in this case, this will be example number 1. This will be example number 1, and a practical question that would be asked in a problem like this might be, what is the normal force? Now recall from our previous lesson that the normal force is any force acting perpendicular to the object due to the surface of what the object is on. Okay, so we've got a cart that's simply sitting here. It's just sitting on a plane. Step one in free body diagramming, in order to answer this question, we have to look at all the forces that are acting on the object. So now we bring in our complete understanding. Step one, create a free body diagram. Part A, identify your IJ coordinate axis. Well, if this, not a coordinate axis, IJ axis. If this cart right here were to move, it would probably move horizontally. And so, I'll call that my I-axis, and this will necessarily be the J-axis. Step two, identify all forces acting on the object. Well, this object does indeed have some mass, and therefore the acceleration due to gravity is acting on it, and therefore the object has weight. Now, weight always acts straight down. Now, I am a big fan. You could call this weight with a vector symbol over it, but I am a bigger fan of calling it what it is. Mass times the acceleration due to gravity. That is an expression of weight. In addition, here's its magnitude. In addition, here's its direction. We see that its head is pointed down relative to our axes, and therefore it has a negative direction associated with it. Now, if this were the only force acting on the object, this cart would fly right through the plane. That doesn't happen, which means the ramp is providing a force also. And based on our axes, we can see that the ramp applies a normal force that is acting up the J-axis. Well, both of these forces, we've ID'd our forces, both of these forces are on an axis, therefore do not need to be resolved. And we have already identified the magnitude and direction for each one of our forces. This is a complete free body diagram of the world's simplest example.